Namaskar. First of all, I'd like to thank and congratulate to the Department of Chemistry, Rajdhani College and Ramajan College for organizing such a wonderful 2-week refresher course in natural sciences. And I must thank to Dr. Banti Kumar, especially that who has contacted me, and then we thought that since it is interdisciplinary in nature, the program, and we should take this advantage to include some of the climatology and the environmental issues which we are doing in Rajdhani College over the last 2 decades. So let me start this. As you see, the topic of my presentation is atmospheric dynamics and its emerging role in understanding the distribution of pollutants. It's perfectly matching with the theme of this online 2-week refresher course in natural sciences. And I must acknowledge my co-workers with whom that we are doing this, and my PhD student and now my colleague in the department, Dr. Vinay Kumar, Dr. Narendra Singh, his scientist in Aries, Nainital, Professor Yodan in Kyoto University, and Shupeng Ho in NASA, Haiyang, Professor Haiyang from Yonsei University, South Korea, and Masaki Takahashi from Tokyo University, Professor S. Hayashida from RIN, Kyoto, and Professor Matsumi from Nagoya University. So this is a group that we are working together, and we have worked on several topics. But I'd like to, I think, in these 30 minutes too, one by one, to introduce you that what is the atmospheric system, what is the thermal structure of atmosphere, and why it is important, the importance of this structure, and of course a little bit chemistry is also involved, and how they are very important and playing a very dominant role in understanding the distribution of the pollutant. So maybe I would like to focus the first 30 minutes in introducing you a very basic and the fundamental of atmospheric structure. Well, as you see that this is a view graph which basically represent troposphere. And troposphere, as all of you know, I mean, that the lowest part of our atmospheric system, the first 15 kilometer, this portion, this layer is called troposphere. And the top layer of the troposphere is basically around like 15, 16 kilometer in the tropical area, especially the countries like India. And in the troposphere, the temperature is basically decreasing from the ground and keeps on decreasing up to about 1500 millibar. And this is, of course, a very fundamental question, that why the temperature keeps on decreasing when you go from ground to like higher altitude. And probably many of us have experienced, and of course we realize that during summertime, you often go to the mountain area. And I give example of like Nainital. So Nainital is about like 2000 meters above sea level altitude. So you remember that there's a little difference in the height and the altitude. So altitude we are taking from the sea level, and height you are taking from the surface of that particular area. So now it is roughly 2 kilometers above if you just compare with Delhi. And there is a term we call a lapse rate. And the lapse rate is something like the decrease in the temperature with altitude. And in this case, this is roughly like 8 to 9 degrees centigrade per kilometer. So these are like 2 kilometers. And it means the temperature difference between Delhi and Nainital should be around like 15 degrees centigrade. So now we also realize that the temperature is decreasing. It is not increasing when you go in the troposphere from the ground to the higher altitude. I would like to mention once again, I think in coming view graph, that what are the basic region behind it and how we can really connect this with the student by giving some simple example. Another, let's proceed, little bit more from troposphere to another part we call stratosphere. And this is another big layer of atmosphere. It's a comparatively stable layer. Stratosphere means the things are stratified. They are stratified. Troposphere is like a more turbulent part of atmosphere. And in the stratosphere, the temperature basically increases with, with height. And it is happening because of the presence of the ozone. There is an ozone layer between 20 to 30 kilometers. So a lot of chemistry is involved here between 20 to 30 kilometers. The radiation budget of atmosphere is basically controlled by the ozone structure. And then if you move further, like 50 to 85 kilometers, then again temperature starts keep on decreasing because the ozone is missing. Again, we are having the same situation. And then we are having ionosphere around like 80 kilometers. So ionosphere was um, very important part, has been very important part during 60s and 70s when a lot of observations were made to understand the D region, the ionization. And this ionization happens because of the solar radiation when they enter. They basically ionize during daytime, our oxygen and nitrogen specifically. Of course, we are having some others thin layer of like Fe and water vapor content. They are available in a very thin layer around like 85, 86 kilometer, 90 kilometer. And then temperature again keep on increasing. So this is a general scenario and of atmospheric structure. Now I proceed further. I think this is a very important um, diagram, which is representing this lower and the middle atmosphere. When I say this lower atmosphere is something like which is related up to like 15 kilometers from meteorology point of view. And the middle atmosphere is like 15 kilometers to 100 kilometers. But to be more precise, I think atmospheric physicists consider 10 kilometers above up to 100 kilometers middle atmosphere. And the first 10 kilometers is a part of lower atmosphere where cloud formation takes place. And then we are having many other chemical species, a lot of pollutants and injection of like volcanic eruptions, a lot of SO2 is injected. So these all things are happening in the lower atmosphere. But once all these things they enter in the stratosphere, as I mentioned earlier, that stratosphere is basically a stable part. And if something happens and something transfer there, then it stays for a long time. For instance, I give you one example of like sulfur dioxide. If it is injected in tons in the volcanic eruptions, and if it stay there like for 2 years or 3 years, the entire radiation pattern changed. The chemistry is also changed. And hence, on the long-term basis, the climate dynamics is also changed. So these are the sequence and the linkages that something happens at one place, but it impacts the climatic system or the environmental conditions over a long period of time. So just focus here. It's a very interesting diagram which is made using by 40 years of the data from 1979 to 2018. And this data is a basically model plus observations together. And this entire data is averaged 40 years of data. Remember, it's a huge data set. And then we try to understand that how the thermal structure look like of atmosphere. So I'd like to mention, just take a couple of minutes around here. This is temperature on x-axis. Here is 0. Then we understand that in the equator, equator means like you are talking about like 5 degree or north and 5 degrees south of the equator. We have averaged this particular profile. And on y-axis, we are having, this is a pressure, and the pressure is from 1000 millibar is going up to 1 millibar. So around here, 100 millibar you can see around here. So 100 millibar is corresponding to like 16 kilometer. And in the first 15 or 16 kilometer over equatorial region, you can see around here in this part, it decreases. And the decrease I mentioned already is about like 7-8 degrees centigrade per kilometer, it decreases. And then it starts increasing from 100 millibar up to like going up to like 40 kilometer roughly. So let me describe you that what does it mean that around 300 to 100 millibar is around like 10, 12 kilometer, then 16 kilometer, 50 millibar is around like 20 kilometer, 10 millibar is about like 32 kilometer, around like 40 kilometer and 45 kilometer, something like this. So this is a very important diagram. You can visualize that temperature is sharply changing above 100 kilometer. Now you look on the right side, this is the polar region. And in the polar region, you can see that it is of course in the negative, but the kind of the kink which you are having on the equator is completely missing here. It is getting more flat, vertical, and then there is a slight increase in the temperature. But this kind of the difference in the temperature is very much visible. Means that is basically difference. And the lowest point, the coldest point is at lower down 300 millibar. That is about like 8-9 kilometers. Around in the equator, 100 millibar, the temperature is about like -80, -85 degrees centigrade. And then above, of course, is, as I mentioned, is going flat. So this is a clear-cut difference between the polar region and the tropical region or equator, you can say. But what is happening in between? In between, we are having the middle latitude, and the middle latitude means you just think about Kashmir is our like part of the middle latitude, the Central Asia part of the Europe, and if you move towards like Beijing area, then Korea, the part of the Japan, and take a full turn of the globe, and this temperature structure is in between these two profiles. So that is the middle latitude. So now, until now, I mentioned that this is the thermal structure of our atmosphere up to like 40-50 kilometer vertically. And now let me tell you that how do you think about if you want to take a snapshot of the vertical wind and the north-south wind, I mean pole to pole, I'm talking about pole to pole. And this is again a remarkable picture figure which is created by Dr. Vinay Kumar. And this is 40 years of the data. I mention again, and you can see around here that this is V means north-south, that is meridional. Of course, we also call like pole to equator. But there is another term we call zonal component, which is east to west or west to east. So these are called. So if I say zonal and it is positive, it means it is eastward. And if it is negative, it is westward. In case of like meridional circulation, that is north-south circulation, positive means northward, negative means southward. So just focus your attention here that on the x-axis, you can see that 0, -20, 40, this is in the southern hemisphere, and 0 to 20, 40, 60, 80, this is in the northern hemisphere. And we just try to give you some basic idea that in the troposphere, there is a heating, solar radiation. And because of the heating, you can understand that there is a divergence. It is the air mass is going up slowly, slowly and diverging and coming down. So this is the actual position. All year, I mentioned again that this is 40 years of the data. And around here, like 8 to 10 degree north, there is a upward motion here. And the upward motion continues up to like 100 millibar. And then it is coming down. So this is what we call the headless cell. So it is something like you take a picture every day and then you connect all these pictures in sequence so you can generate this kind of the figure. This is what we call the headless cell, and it is coming down one branch around here. Then you are having feral cell. So there is another motion around here around 60 degree north going up, and it is coming down, mixing here and then around here. So these are the three major cells we call headless cell, feral cell, and polar cell, which basically represent or control the first 15 kilometers of the Earth atmosphere. Very, very important. The similar features you can see in the southern hemisphere, similar exactly going up, coming down, going up and mixing this side. So we all understand that when the things are going up, there is divergences, adiabatic expansion. So naturally, there is a strong cooling around here. And because of the cooling, it is getting heavy and then it is coming down on both sides. So these motions, they are present throughout the year, and they are very important to decide about the large scale motions in the Earth atmosphere. Also, they are very important to understand the monsoon system and the climatology and vertical motions, horizontal motions. And when this entire dynamics is so important, it also decides when there are some injections of like trace gases or pollutants, it goes up, it basically redistribute that as per the choice of the dynamics, which is shown here. Let me explain you that what is the seasonal march in this case. So this view graph is seasonal march of the vertical and meridional wind patterns. And it's a kind of climatology, as I mentioned already, that this is a 40 years data. You can visualize, if you just close your eyes, you can see that the wind, the vertical motions, vertical wind. And I'd like to mention here that only radar can take observations directly for the wind, and there is no any other instruments. Of course, you can compute that indirectly, but the direct observations can be made only by the radar. I will show you some of the pictures later in this presentation. This is October, then November, and December. So I would like to mention here that this kind of like path around here, then this is very close to between 0 to 20 degree, 10 degree north. Then it is shifting here towards equator, then again shifting here. So there is a seasonal shifting towards equator if you move from October to November to December. And I'd like to mention here that this kind of the shifting is also important to correlate with the long-term changes, long-term motions of atmosphere, whether they are regional motions or they may be planetary scale motions. You can see the bottom panel around here. This is March, April, and May. So the shifting, as I mentioned here in the December, it was very close to 0 degree north. I mean, this is very close to equator. And then there is a shifting, and then it is coming back again to May, shifted between 0 to 20. And then if you take data of June, July, August, so then it is just moving back and forth, back and forth. So, and it is very important to connect northern and southern hemisphere. And also, I did not show here the large scale motions which are planetaries in scale. We just average the entire Earth and just have shown only the north-south cross section. So let me tell you that, and maybe very important for the students, that what are the physical equations, which is very important to understand for atmospheric dynamics. So this is the first equation we call hydrostatic balance equation. dP by dz is minus rho g. What is this dP by dz? P is the same like you talk about the pressure, H rho g. And if you just differentiate this with respect to altitude, you are getting minus rho g. So remember, very important hydrostatic balance equation, and that is the base of the existence of atmosphere, because you have seen in the previous diagrams of the figures that the pressure is very high at the bottom side, and pressure keeps on decreasing. You go up to 100 millibar. So at 16 kilometer height, the pressure is 100 millibar. At the ground, it is 1000 millibar. So it is 10 times less. So there is a vertical pressure gradient which is acting upward. On the other hand, there is a gravity which is acting downward, and both forces balancing each other. And we have put negative because both are acting in the opposite direction. So this is a basic fundamental idea that how this atmosphere is balancing. If there is no two forces acting like in the opposite direction, probably the existence of atmosphere could have gone. On the right side, I have defined the potential temperature. This is a field parameter and very important. And this is equal to T, that is our actual temperature at a particular pressure level. And P naught is the pressure at ground, that is 1000 millibar. And let's say you want to calculate what is theta, potential temperature at 100 millibar. So P would be 100 millibar, and R by Cp, these are the constant, which is given around here. R by Cp is here 0.286. And based on this, I'd like to define one more term we call Brunt-Väisälä frequency. And this is defined by n equal to z by theta, d theta by dz, power half. And this is give you some idea about the stability of the atmosphere. And it is something like there is a natural oscillation in the atmosphere. It is similar. I think you can understand that, like in the lake or maybe in the pond. So there are always ripples. They are moving on the top surface, and they are having a simple periodicity of like a few minutes. Similarly, the atmosphere, the troposphere and the stratosphere, both they are having a natural vibrations, natural oscillations, and they are roughly like 10 minutes. And in the stratosphere is about like 6 minutes. So if you want to inject or allow to propagate another atmospheric wave oscillation, then definitely the time period of that oscillation should be greater than this Brunt-Väisälä period. And one more thing, which is very important, if the value of n is negative, then it means it is not defined, undefined. So it is a turbulent atmosphere. And if the value is 0 or greater than 0, then it is a stable atmosphere. And this is very much, I think, applicable in the stratosphere. The values are larger, greater than 0, and you are having positive values. So we can use radius on the flight. Radius on the flight means daily in the meteorological department launching balloons from about like 40 stations in India. One in the morning at 5:30, and second is in the evening about 5:30. And based on those, you can calculate the stability of the atmosphere vertically based on this kind of a formula. So what are the other observations technique? So these are like which has made possible. I'm just talking about that how the things really progressed over the last 2-3 decades. So we started about with the rocket, like in the mid 60s, 70s, and even up to 2000. Indian Space Research Organization is to launch some observational for observational purposes some rocket experiments we conduct very often. Then the balloon is another one. So we are having some very special balloon which can go up to like 40 kilometer, 50 kilometer height. They are specially designed, and you can put some sensors. So these sensors can go up to that particular level, and then you can get information from the atmosphere by using sensors. Then radar is another technique, and as I mentioned earlier, that the radar can directly take observations of the vertical wind when you operate this. So this kind of radar I'm talking, these are very powerful radar. They don't require object like maybe in the olden times of the Second World War it started, that they were used to detect aircraft. But aircraft is very bigger object these days. We don't need anything. If you just operate in the open air, then the radar can get backscatter from the refractive index variability. And you can, using this backscatter, you can easily find out the wind component, UVW component, and at a very high resolution, time resolution and height resolution. So after every 2 minutes, you can tell the data. And therefore, you might have experienced that recently, the weather forecasting has improved a lot because of these factors, because we are having the observations, and these observations, they are basically put in the models, and you can run the models, and they can give you prior information of weather forecast for another 5 to 6 hours at a very it's a great accuracy, we can say. Now let's see about another part, that is lidar. So lidar is another good component which we can understand. This is basically a laser technique, and you can run lidar during nighttime, because during daytime they can interfere with the sunlight and cannot be operated. So radar can give you a wind component, satellite can give you thermal structure, lidar can also give you up to 90 kilometer the temperature, background temperature. So if you are having all these atmospheric parameters, we can put them together, you can run the model, you can calculate all atmospheric parameters, about 15, 16 parameters. And these are very important to understand the weather conditions. You can understand the transport, you can understand the radiation pattern, you can understand about the fog formation, and whether it will be clear or wind speed kitna hoga. I mean, there are a number of things you can do. So I show you some examples. I think a few years ago, I visited Nainital, and this is one of the sample of this radio sound. And if you can see the string, and here it is lying the sensors. So it carries the sensors, and then you get the data. It's a GPS receiver we are having on the ground. So every 10 seconds, we are getting data, even better than that, and at a very high resolution, altitude-wise and time resolution. So, but basically, these balloons, they go up to like 40 kilometers, and you know, when it goes up high and high, the outside temperature, pressure keeps on decreasing, and the internal pressure of the gas is a hydrogen gas inside. It bursts because of the difference in the pressure, and then sometimes we put parachute here, and or of course there is another problem which I would like to mention here specifically. In the background, you are having a strong wind, like at 10-15 kilometer altitude. The wind is about like 30 meter per second, 40 meter per second. So the balloon drifted very often to long distance, like 200 kilometer, 300 kilometers. So they often reach to Nepal, and sometimes they burst and they carry these boxes. So we can retrieve them, and they put sometimes some kind of like incentive. If somebody return to this particular address, they will get 500 rupees or 1000 rupees, and we can use them again. So the basic idea ultimately is that they are a bit expensive. You can launch this like having 40,000 rupees or 50,000 rupees, but it is really expensive affair. Therefore, we have to keep a sustainable instrument, and radar is that option. So, but let me show you some rocket sounding from Tumba, which of course I did my PhD work based on this Tumba rocket and Balasore and Shar. And this is a VHF radar antenna view at Aris Nainital. So this is a roof, a top roof, and you can see, so there are about like 600 antenna. They are phased array antenna, and you can run this radar and you can get data, the wind data, at a very high time resolution. Means after every 2 minutes you can get data, and for every 75 meter to 150 meter you can get vertical data, and you can run this 24 hours. So in India, of course, ISRO, when there is a launch of satellite or some big launching program of like Mars mission or any other mission, then the radar is operated. That radar is basically installed at near Tirupati. There is a place we call Gadanki, and this is ISRO lab, and it is operated a couple of days in advance so that you can give prior information about the actual weather conditions, so that this safe takeoff can be made from Sriharikota. So this is itself is a subject itself, like radar physics. So in the radar physics is a full paper. So we can spend a couple of hours on this, but this is just, I would like to give some brief idea that how these big radars, they are operated. And just I take a couple of minutes here to spend, because the cost of this radar is very high, about like 15 to 20 crore rupees. And in India now, India Meteorological Department or Ministry of Earth Sciences has deployed Doppler weather radar also, means along the coastal area on both sides, and you can provide data frequently to the model of NCMRWF, which is located in Noida, and we call this a medium range weather forecasting. It's a National Center for Medium Range Weather Forecasting. So some basic idea that it sends the beam, the electromagnetic pulse in the atmosphere, and it get the backscatter only from change in the refractive index in the air. And that backscatter is enough to, that small amount of the backscatter radar power is enough or sufficient to process the signal. And the signal is coming in the form of the Doppler shift of frequency. And this Doppler shift can be utilized to compute your wind component. And then this wind component can be utilized later for model and everything. This is a view of lidar observations. So these green color lidar, they are operated in the night, and you can, based on this like density variability, and we can convert that into temperature. So you can find out the temperature all along up to 90 kilometers. There are few types of lidar, Me radar, Raleigh lidar, something like that. And they are operated, they are fit for a particular aspect. Some of them, they may be good for taking observations for the cloud droplets, and some of them, they can pass through this and can go very high altitude up to like 90 kilometers. So internationally, there have been some groups who are operating LiDAR over the last 3 decades or 4 decades or so. So this is satellite observations for taking the cloud tops, observations that what is the height, what is the altitude of the clouds, up to means which particular depth it can go. And then maybe I can show you one example and then I stop here. This is an example of cloud top. the top panel, and this is from equator to polar region, 10, 20, 30, it means tropical area. And I would like to mention only one thing here, that you can see the top of the cloud goes up to like 15 kilometer in the tropical belt and equator. But the moment when you cross this 30-degree north or reaches to 40-degree north, the top of the cloud basically reduced and it comes down. And this is something like about like 10 kilometer or so. And this you can correlate, which I shown the first view graph of temperature profile of equator and temperature profile in the polar region. So this is the basic difference, and hence the cloud formation, their vertical growth, horizontal growth, and motions, they basically are controlled by that. So this is my part one, and I would like to mention part two, that what is their role for distribution of the pollutants. Thank you.